Hello friends, Mr. Burrell here. We're in Unit 3. We've been talking a lot about parallel lines and all the different angle relationships that pop up when we're talking about parallel lines and a transversal cutting through. We've talked about what each of those different relationships are called. We've talked about solving different types of algebra problems using what we know about those relationships. Now we're going to be talking about proofs, and I'll explain a little bit what those are. I throw that word around. I've thrown that word around a few times in the last few lessons, so now we're going to formally define what that really means. So by the end of this lesson, I would hope that you are able to use these theorems of parallel lines that we've discussed to prove different statements about parallel lines. When I say theorems, these are the things I'm talking about, these different angle relationships that we have discussed and that we've already determined are true. We're going to use these truths to show or to prove other truths about parallel lines. So what is a proof? Anyways, when I say that word, what do I mean? Formally, the definition is a geometric proof involves writing reasoned, logical explanations that use definitions and previously proved theorems to arrive at a conclusion about a geometric statement. That's a lot of words. To sum it up, a proof is just using theorems and relationships we already know to show that another statement that we don't know yet is actually true. So we use what we do know to show that something else is true. Okay, so many of you have probably played Uno before. I'm going to go over the rules real quick of Uno, and then I'll give you an example. I'm going to use Uno to explain how we write geometric proofs. So for example, if in my discard pile I had a blue 8, and I have all of these potential cards to try to eventually get to a yellow 3, how do I get there? How do I get from the blue 8 to the yellow 3? Well, in Uno, you can either place numbers on the same numbers or colors on the same colors. So on top of this blue 8, I can play this green 8. That's legal. On top of that green 8, I could play this green 1. That's legal. And on top of this green 1, I could play this yellow 1. That was a really good arrow. I could play this yellow 1, and then I could play my yellow 3. I have these 3 cards at my disposal, and I was able to use all of them to get from point A to point B. And they were all connected to get from the blue 8 all the way to the yellow 3. So let me show you another example here. How can I get from the red 2 to the blue 5? Well, if I wanted to use every card, I'd probably use this wild to change it to a red, or sorry, not to a red, to a green. Then I'd play this green 4, this green 8, and then this blue 8. That's one way I could go about this. Change the red to green, and then a green 4, green 8, blue 5. I have all 4 of those cards at my disposal. I could use all 4 of those cards to get from the red 2 to the blue 5. Do I have to use all 4 cards? No. I could just use this wild and change it to blue, and then put the blue 5 on top of that. Are either of those ways wrong? When I used all of these cards or just one of these cards, are one of those more correct than the other one? No. I used all of my cards in one situation. That's fine. That's a way to do it. It takes more cards, but it all works. Or I could just use one card. It's shorter, but not any better than the other way. I had 4 tools. All of them I were able to use. Okay. This one, how do I get from the blue 0 to the yellow 7? Well, if I'm trying to use all my cards, well, this is the way I would do it. I would do maybe a red 0, and then a red 2, red 7, and then yellow 7. That's not the only way you could do it. You could eliminate this red 2, just go straight from red 0 to red 7. That would work. I have this 5 here, but notice that's not helpful at all. I don't even use it. I can't use it. It's there. It's in my hand. I have that card, that tool available to me, but it's not very helpful in trying to get from point A to point B like I am here. So why are we talking about this? Why am I discussing this? Well, these moves, these logical steps we make in an Uno card game are very similar to the logical steps we make to complete a geometry proof. Let me give you an example. Earlier, I had a bunch of different kinds of cards in my hand. I had a blue 5, a red 0, a red 2, a red 7. I had all those tools, all those cards at my disposal to get from point A to point B. When we're talking about parallel lines in geometry, these right here are the quote-unquote cards I have in my hand. those are the tools that I can use to get from point A, what I'm given, to point B, what I'm trying to get to. Because all these things we've already discussed. We know all of these things. We know alternate interior angles are congruent. We know alternate and exterior angles are congruent. We know consecutive interior angles are supplementary. We know these are congruent. We know these are congruent. We know these are supplementary. We know all these things. We've already discussed them. So they are theorems that we can use to prove other things that we may not know yet. So let me give you an example. Here's a proof. I'm given that L is parallel to N. That is my very first card. That's where I'm starting. I know that L is parallel to N. Where I'm trying to end is with this. Measure of angle 3 plus the measure of angle 6 is equal to 180 degrees. So first of all, do you think that's true? Do you think angle 3 and angle 6 are supplementary angles? Do they add up to 180 degrees? I would say yes. Specifically, how do we know that those are supplementary angles? Well, right here, one of the tools in our toolbox, one of the cards at our disposal, is that consecutive interior angles are supplementary. Well, let me put that card right here. 3 and 6 are consecutive interior angles and are supplementary. So this is how my proof would go. Since I know L and N are parallel, then I know 3 and 6 are consecutive interior angles, and therefore they're supplementary. Therefore, 3 and 6 must add up to 180 degrees. And that's it. You just showed me, you just proven to me that that statement is actually true. The measure of angle 3 plus the measure of angle 6 is 180 degrees. This is how I typed it up. Mine's a little bit more excessive, a little bit longer than yours would need to be. But here are each of the things that I discussed. We were given that lines M and M are parallel. That's what we started with. So if two parallel lines are cut by a transversal, then consecutive interior angles are supplementary. That's a tool that I have at my disposal. That's a card I can play. Since angles 3 and 6 are consecutive interior angles and therefore supplementary, they add up to 180 degrees. So 3 plus 6 is equal to 180 degrees. That's an example of a pretty short, pretty simple, pretty straightforward proof. So let me give you another example. Well, first, each of these proofs that you write, they're going to be in this sentence or paragraph form. Just like you were talking to a neighbor or you were writing to your math teacher, convincing them of this geometric principle. This is how you would write it out. So let's look, I want to look at this example. Okay, so I'm given that M is parallel to N. So these two lines are parallel. That's where I'm starting. That's the first card that I'm given. M is parallel to N. That's what those train tracks mean. M is parallel to N. Where am I trying to get to? What am I trying to prove? Is that angle 1 and angle 3 are supplementary. So the very last card I'm trying to get to is 1 and 3 are supplementary. That's where I'm trying to get to. So keep in mind that I have 6 tools in my tool belt. 6 cards in my hand. Alternate interior angles are congruent, alternate exterior angles are congruent, etc., etc. Let me backtrack back so you can see them again. These right here, those are the 6 tools I have in my hand, the 6 cards I can use. So let's put them, the ones that we need to, in a certain order so that we can get from point A, the fact that these two lines are parallel, to point B, the fact that 1 and 3 are supplementary. So there's several different ways you could go about this. Right here in this image, they've numbered these angles as 1, 2, and 3. So we need to kind of think of how all these are related. How are we going to use my cards to transform from M is parallel to N all the way to 1 and 3 are supplementary? Well, this would be my thinking. If I'm starting with angle 1, because I have to start with one of these angles, if I start with angle 1, I don't have a theorem that tells me anything about angles 1 and angle 3, but I do have a theorem that tells me something about angle 1 and angle 2. That's a start. That's one of my tools. What do I know about these two angles? 1 and 2 are corresponding angles. And corresponding angles, when lines are parallel, are congruent. So the first card that I know that I have at my disposal that I'm going to use is 1 is congruent to 2. That's what this little equal sign with the squiggly over it means. That's a congruent symbol. 1 is congruent to 2 because corresponding angles, this is angles, are congruent. That's my first sentence in my paragraph proof. 1 is congruent to 2 because corresponding angles are congruent. But I'm not done yet. I have to get all the way to 3. Well, I know 1 is congruent to 2. How is 2 related to 3? This is an angle relationship, I know. This right here is a linear pair. And linear pairs are supplementary. So 2 and 3 are a linear pair and therefore supplementary. So I've used the cards in my hand, the tools that I have used so far, supplementary, are corresponding angles are congruent and linear pairs are supplementary. Those are the 2 cards that I have used. I had lots of other cards that I could have used. I didn't necessarily need to. These are the only ones I really needed to use. So if 1 and 2 are congruent, and 2 and 3 are supplementary, that must mean that 1 and 3, right here, are also supplementary. So that right there is my proof. So if I were to write this out in paragraph form, this is probably how I would write my proof. Since lines M and N are parallel, 1 and 2, angles 1 and 2 are congruent to each other because they are corresponding angles. Also, angles 2 and 3 are supplementary because they are a linear pair. Therefore, angle 1 and angle 3 are supplementary. And that right there, what I just said, the words that came out of my mouth, if you need to rewind this and watch it again, that would be my proof. So there's lots of different things like this that you can do, that you can prove. This example is, if you're in my class, is in your guided notes. And this example over here is in your homework packet. So you can try those on for size as well. You can rewind this video to each of these points so you can look at these and you can try them out. But really, when we're writing these geometric proofs, we're just taking logical steps from point A to point B using the tools that we already have in our arsenal, that we've already talked about and discussed that are true, to prove other things, to convince ourselves of other things that we don't know yet. And that's what really geometry and math is all about, proving that certain things are true and making those logical connections. So I hope that was helpful, and I hope you enjoyed that as much as I did.